Hello and welcome to the Data Engineering Podcast, the show about modern data infrastructure. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at www.dataengineeringpodcast.com/Linode and get a $20 credit to try out their fast and reliable Linux virtual servers for running your data pipelines or trying out the tools you hear about on the show. Go to dataengineeringpodcast.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. And to help support the show, you can check out the Patreon page, which is linked from the site. To help other people find the show, you can leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. I've got a couple of announcements before we start the show. There's still time to register for the O'Reilly Strata Conference in San Jose, California, happening from March 5th to the 8th. Use the link dataengineeringpodcast.com/strata-san-jose to register and save 20% off your tickets. The O'Reilly AI Conference is also coming up, happening April 29th to the 30th in New York. It will give you a solid understanding of the latest breakthroughs and best practices in AI for business. Go to dataengineeringpodcast.com/AICon-new-york to register and save 20% off the tickets. Also, if you work with data or want to learn more about how the projects you have heard about on the show get used in the real world, then join me at the Open Data Science Conference happening in Boston from May 1st through the 4th. It has become one of the largest events for data scientists, data engineers, and data-driven businesses to get together and learn how to be more effective. To save 60% off your tickets, go to dataengineeringpodcast.com/ODSC-East-2018 and register. Your host is Tobias Macy, and today I'm interviewing Sam Stokes about his work at Honeycomb, a modern platform for observability of software systems. So, Sam, could you start by introducing yourself?
Hi there, my name's Sam Stokes. I'm an engineering manager at Honeycomb. Honeycomb is a pretty small B2B startup in the Bay Area, and I've been at Honeycomb for almost a year now.
And do you remember how you first got involved in the area of data management?
I got involved sort of by accident. So I've been, for most of my career, I've been an engineer who has occasionally pretended to do operations. And I've, for a while, thought that I really needed a tool that would let me use my engineering instincts to help me solve operational problems. And so when I saw a demo of what Honeycomb was building, I sort of stopped them 30 seconds in and like, yeah, okay, I get it already. This is the thing that I've been needing for years. How can I help? And they were like, great. Well, we built our own data store and we really like someone to help maintain it. So you can do that. And I was like, oh, okay, sure. I guess I'm a data engineer now. So yeah, I found myself maintaining a custom data store implementation. And it turns out if you carefully scope what it is that you're doing and you make it very clear that you're not building a general purpose database, that it's not as crazy a thing as it sounds to do that. But yeah, it's definitely been a learning experience of okay, this is what it means to actually be in charge of a data store implementation and a significant amount of customer data.
Yeah, the sort of general wisdom is the first rule of building a database is don't build a database. But the second rule is that if you know that you really need a database, then go ahead and build it.
Yeah, and if you have to build a database, well, call it a data store, because then people don't think you build a database.
And so you've mentioned briefly that Honeycomb is a tool for being able to get observability into your software systems. And I'm wondering if you can describe a bit more about what Honeycomb is as a company and what you mean when you say observability.
It's a great question. So what Honeycomb is, it's easy to explain what Honeycomb does. What Honeycomb does is we let you query the events that your own system is producing. So what's an event? Well, let's say you run a web server or a web app that consists of a bunch of components, one of which is a web server. So an event might be, I processed a request from a user, and that request was serve the sign-up page on this server, and it took this long, and the user was on an Android device, and lots of other details that you might have about the processing of that request. So that's an event. So to use Honeycomb, you have your services send us events. Everything that happens is an event that you might want to tell us about. And then we let you run queries on those events. And a query you might want to ask is, how many events did I process this week, per day. Show me a time series graph of my traffic this week. And so we can give you that. You run a count query that just says, count my events over every 15-second interval in the last week, and we can give you a time series graph. But then because you send us all these details along with the events, we can also do things like show me the 95th percentile response time of the events that I served this week for every 15-second interval over the last week. Now you have a response time graph as well. And these are the kinds of things you could get in a traditional operations tool. Now you have traffic and you have latency. You could do errors as well. And then with Honeycomb, you can also ask questions like, okay, given that 95th percentile response time graph, break that down by mobile platform. Show me how fast Android users are versus iPhone users. Or break it down by geographical location. Or show me the top 10 slowest users. And so that's, in a nutshell, what Honeycomb is trying to give you, is the ability to ask these sorts of operational questions about your system, but in a very flexible way, which doesn't require you to sort of predefine a whole bunch of metrics front. And that is sort of what we talk about. That's sort of what we mean by observability as well. It's the ability to ask questions about your system and see what it's doing in real time and in a fairly fine-grained way. My system is doing all these things. I have a web server, I have a database, I have a microservice for doing authentication, I have a microservice for, let's say, verifying that I'm not doing fraudulent activity. And all these things are operating in concert with each other, and one of them is calling the other, and they go up and down independently, and they get deployed independently, and one of them is an API that I'm calling from some other company. How do I know what's going on? I need to be able to look at my system in the same way that an engineer developing software on their laptop would run a debugger against their code or try running it in a test mode and see what happens. We want to give you the ability to do that in production, to just ask, what is my system doing right now? What does normal look like? What does my system look like when it's processing normal load? What changed when I rolled out this new version of software? What changed yesterday when this latency spike went to double normal latency or something like that?
So yeah, there's definitely a lot to dig into in terms of the ways that you can structure the event data that you're sending into the system to be able to then gain interesting insights out of it. But for the time being, I'd like to focus on the path that the events take from the client system all the way through your data infrastructure to the point where it's being rendered out as a data point on a graph for somebody who's trying to debug a systems issue, and the different systems that you use to be able to manage that event data.
The lifecycle of an event looks like this. First of all, the system that is processing an event, the system that is originating an event, needs to tell us that an event happened. So we give you a few ways of doing that. We give you, we provide SDKs, which you can use to instrument your own code if you're running code that you wrote and you have access to add instrumentation, in which case you have an SDK which will let you do things like emit an event that this thing happened with the following properties. So that's one way that you can send us an event. We also provide an agent which can take, if you're outputting things to log files, we have an agent that can tail those log files and parse them into structured data, which then gets emitted to us as events. So one way or another, you send us an event. That looks like making a post request to a web service that we provide. So you send us an event. Events look like JSON blobs. So they have a bunch of different properties. Property might be the response time something, which should be numeric. It could be a string, what path did you hit in the web server? It could be, any property about what server was running this event. So you post that to us. We have a service that sits on that receives all the events and basically just dumps them straight into a Kafka topic. So we rely pretty heavily at Honeycomb on Apache Kafka, and all our events through one big Kafka topic that's partitioned into lots of partitions. And consuming from that Kafka topic, we have a service that we call Retriever. Retriever is our custom data store. So Retriever consumes events from the Kafka topic and stores them onto disk. We can go into some interesting things about the design of Retriever, but basically Retriever stores events on disk. We store every single event that you send us, and the idea behind storing every single event is the only way to let you ask questions about your events in a flexible way, other than having to sort of decide what you're going to pre-aggregate and ask questions about up front. The only way to let you ask questions flexibly is to just store everything you send us and then query them all and do any aggregation. So if you're asking, give me the average of something, we compute that average at the time that you ask the question. So Retriever does two jobs. Retriever consumes from the Kafka queue, receiving events as they come in and writing them to disk. And then Retriever also serves queries. So when you run a query, that gets sent to our web service. Our web service forwards the query on to Retriever. Retriever reads events off disk according to the query parameters that you specified. And let's say you were asking about something like, give me the average response time of all events that were served from an Android device. So Retriever will read all of your events and apply that filter, so it will read event by event, discarding any event that wasn't read from an Android device, and it will keep track of the response time of each event and keep track of the number of events that it read, so that once it's read everything, it can sum up all the response times and count up all the events, divide the sum by the count and the average, and then serve that back up, for example, in a time series, if that was the query that you were running, and then you get a graph out at the end. And then we have a pretty rich visualization system, which can take those graphs and render them in lots of different ways, and let you do things like compare different breakdown groups against each other.
And so, as you mentioned, the data that you're posting into Honeycomb is just JSON. So I'm wondering if you can describe a bit about the characteristics of the event data that you're dealing with and the challenges that it poses when you're dealing with large volumes of it, particularly given the fact that there isn't necessarily any inherent structure to it. You may be dealing with sparse data because not every event is going to have the same keys in it to be able to look up.
So the nice thing about column-oriented storage is that, let's say you're asking a query, you're running a query which is something like, give me the 95th percentile response time of all events that had no error. So you could serve that from any kind of storage engine, right? You run over all of the events, you run some filter. The advantage of column-oriented storage is all of those other fields, the path, the server name, the mobile platform, I don't need to read any of that data when I'm answering the query of show me the 95th percentile response time filtered by there not being an error. And that sounds pretty good for the example that I gave, where I have maybe 6 fields and I only have to read 3 of them. But it's quite common for us to get events that have 50 fields or 100 fields. And so that means we're disregarding about 90% of the data that you sent us for most of the queries that you're likely to run. And it turns out that's a really big speed up, because a lot of the cost of running this kind of analytic queries is the I/O cost of just reading the data back off disk. And so that's one of the ways we deal with this sort of sparse, schemaless sort of data. It's just by storing it in a way where at read time, the schema doesn't matter very much. We only use the schema to tell us what data we need to read according to the query that you ran.
Working particularly in an operations context, but also who are dealing with unstructured data or loosely structured data are probably familiar with systems such as MongoDB or Elasticsearch for being able to handle this schemaless nature. But the advantage, it sounds like, of having the custom-built data store is that the usage patterns that you're dealing with for being able to answer these analytical queries focused on an operations context as opposed to a more textually oriented system like Elasticsearch, which people might use for logs, or a more general purpose queryable document store like MongoDB, where people are looking for the entire document to be returned at once, is that because you're not trying to optimize for doing substring matches with freeform text fields.
Right, exactly. So if we're asking the question of give me the 95th percentile response time, then we know that that's all we need to keep. So we can go event by event, just keep those floats, run a streaming aggregate that doesn't need to use lots of memory because all we're doing is adding 2 numbers together, and then do 1 division at the end. So yeah, we can read massive amounts of data with constant memory usage.
And one of the problems that's often faced when you're working to gain visibility into an operational system is that oftentimes it can be difficult or time intensive to actually add all of the instrumentation code to the software that you're running or the underlying operating systems or cloud platforms. So I'm wondering what you found to be the most difficult aspects of collecting the data and whether you have any specific tooling that simplifies that work for the end user who's trying to integrate with your system.
This is definitely an area where people have usually invested a bit of effort already, and that can be good for us or bad for us. Often they've invested a little bit of effort into gathering some kind of data from their systems, and sometimes that is helpful because they have just enough data coming out. For example, if they're emitting something into logs, if we're lucky, there's enough structure in those logs that we can run our agent against those logs, parse out in the data to get something useful out, and we can turn that into the structured data that you really want, and then let you query against those. Sometimes people have invested a lot of effort into something like a metrics system, and metrics is something that looks superficially very similar to what we're providing. You end up with time series graphs at the end, and you can compare one graph against another. The problem is metrics is about pre-aggregating things. So metrics, you might say, I saw one request from this user in Europe, and you increment a counter for that, and you add some value to a gauge about, you add an aggregate thing to the response time for that user in that geolocation. If you then want to split that metric by some other field, like mobile platform, well, you didn't gather that data in the first place, so you don't have the data to go back to. So sometimes if people have invested a lot of effort into instrumenting the code for metrics, we find that they don't want to go back and do the effort again in order to emit structured data so that they can send it to us. So yeah, instrumentation is something that it's hard to get away from. You have to put some effort into instrumenting your code. However, you can often exploit details of the platforms that you're running on. For example, if you're running on a web framework like Rails or Django, they tend to provide a lot of structure around this kind of thing already. If you're running arbitrary software, there's all kinds of stuff you could be doing, but if you're running a Rails app, then you know that your system is mostly processing web requests, and that every web request has a bunch of properties which the framework knows about. It went through this code component, it hit this particular endpoint, it took this lot of run, it spent this long talking to the database, it spent long talking to the template rendering layer, it rendered this particular template. It was done on behalf of this user. So if you have structure in your system that you can make use of, you can often get a lot of instrumentation with a lot less effort. And we're looking at how we can provide better tooling that can sort of take advantage of that structure that's there. In the absence of instrumentation, there are some things that you can hook into at the platform level. So one example, if you're running on a runtime platform like Heroku, again, Heroku gives you a lot of logging and instrumentation just by virtue of how the Heroku platform is architected. So you can subscribe to their logplex system, which emits all kinds of event data about every request that gets routed in, and they emit product metrics of using their database product. If you're using a platform like Kubernetes, there's lots of telemetry that gets emitted from all of the different components of Kubernetes that we can use to get an idea of what's going on in your application. But the real power is being able to tell us not just the generic details, every web application is processing web requests, but what is unique to your business or the problem that you're trying to solve. User ID is an obvious thing. If someone's logged in while you're processing a request, then it's really useful to tell us what's the user ID, what's the characteristics of the person that you're performing the request for. But maybe your business is dealing with shopping carts. Maybe you don't care so much about the person who's logged in. You do care a lot about how many items they had in their cart, or what product they were looking at when they clicked on a different product, or something like that. And that's something that is really, really powerful when you have access to that sort of data. If you can say something like, if you're troubleshooting some kind of performance issue in your site, in your e-commerce site, and you can say, it looks like it was running slow, show me the top 10 slowest products that were involved in people's shopping carts. Maybe you've got some product that's really popular and lots of people are looking at it and that's blowing out some cache somewhere. That kind of thing is really powerful, putting a business level piece of information into your operational data. But that's really impossible to do unless you can write instrumentation. So it does come down eventually to showing people the value they can get out of instrumenting a code so that we encourage them to do it.
We've been focusing a lot of the discussion on being able to gain observability into user-facing systems, but it seems like this would also be a very useful tool for somebody who's doing more of a data engineering workflow where you could potentially emit the various events from different stages of Airflow jobs to be able to gain visibility into how the health of that system, or being able to track some attributes of your data ingestion pipeline to make sure that that's functioning properly. So I'm wondering if you can talk a bit about some of the ways that Honeycomb benefits that type of workflow.
Absolutely. I can give one example from our own internal usage of Honeycomb. We were trying to roll out a new storage method in our own internal data store. The same thing I've been talking about with Revo. We wanted to change the way that data store stored strings. And I won't go into the details of what the change was, but it's a change to the way that we took events and stored them on disk. And we wanted to roll that out in a fairly cautious way because we were processing a lot of customer data. We wanted to see if there's going to be any performance impact. So we use feature flagging as a practice reasonably consistently at Honeycomb. We use a service called Launch.ly, which is a feature flag as a service. And the way we decided to roll out this storage change was to put the change under a flag and then flag it to 10% of customer datasets. And this was a change that, in theory, was just under the hood, that customers wouldn't see the difference. We just wanted to see, was there a performance change? So we flagged out the change to 10% of datasets. And then we just ran it for a week and let us gather data about the performance of our own system. And then we could start asking questions. What does this thing look like on both sides of this flag? What does the average time to write a record look like for datasets that have this new storage feature turned on versus datasets that have this feature turned off? What does the average size of data look like for things on both sides of this flag? So yeah, that's one example where, again, it's useful to be able to break this down by lots of different facets. One thing we found was that at one point we decided that this 10% rollout was going well and we wanted to roll it out further. So we flipped from 10% to 9%. And we found that the change was supposedly neutral. We didn't think there was going to be a performance impact, but when we flipped from 10% to 90%, it seemed like a lot of things got slower. A lot of metrics that we were breaking down this flag got a lot slower. And we're like, wait, this doesn't make sense. We didn't think this would have all this impact. So we did a lot of head scratching and then eventually thought, well, what did we actually change? We went from a scenario where 10% of our customers were on this old system and 10% were on the new system and 90% were on the old system. And then we switched over to most of the customers were on the new system. And what we realized was one of our largest customers, who was writing a much larger volume of data, had not been in the 10% that we'd chosen. And that customer was doing all the metrics. And so because they were in the majority, when the majority had the old system looked slower. But once we switched the new system to being the majority, the new system looked slower. The difference actually was nothing to do with whether the change was in effect or not. It was just what side of the flag was this particular customer on. And that's the kind of thing where only because we could break this down by customer could we reveal that difference. So we could see this apparent change in performance. But then when we broke the performance graph down by customer ID, we could see, oh right, now we can correct for this difference. We can see who's on what side of the flag. So that's one example where having access to more data gives us the ability to see really what's going on. You were asking very specifically about data pipelines, and I think I didn't answer that part of the question. Actually, I have a little more to say about that part if you think that's an interesting direction.
Sure. So yeah, that's definitely very interesting to hear a specific example of how you're actually dogfooding Honeycomb in order to make the Honeycomb service itself run better. So I'm wondering if you have any other sort of anecdotes about using Honeycomb to improve Honeycomb.
We had one example where we wanted to really optimize the performance of our queries. So the core activity of somebody using Honeycomb is to run a query against the data that they sent us. So they go into our interface, they specify a query, we take that query, send it to Retriever queries your events, we send you back a graph. And that wasn't as fast as we wanted it to be. So Fortunately, we were instrumenting our own system, and so we had lots of event data for every query that somebody was running. And so we could ask questions like, what is the 95th percentile time to run a query? And let's say that came back in 5 seconds, so we could say, we're actually doing a lot better than that these days. But let's say that it came back at 5 seconds, then we can say, well, 19 out of 20 queries are coming back in 5 seconds, but we'd like that to be better. So now we can break down and say, well, show me all the queries that are slower than that, and where are they getting stuck? And it turned out that the details of how our front end are, we have a JavaScript web application that's talking to our backend running queries. And one of the details of how that works is it fires off a query to the backend, and then it polls, it just checks repeatedly to see whether the query result has come back yet. And it turned out that a lot of the delay in running queries was just that polling was running too slowly. We were only checking one time every second. And a lot of our queries actually were quicker than that. A lot of our queries were coming back in under a second, but we were still waiting, a second plus the race condition of, we fired off the query and then we decided when to start that second timer. So we were waiting longer than we actually needed to see when that query came back. And that became clear when we could look at the details of the performance profile. And we just dropped that polling time down to something like 200 milliseconds. And suddenly all our queries were that much faster. It might sound like an obvious insight, like if you poll less quickly, but it's the kind of thing where it could just be polling every millisecond, but that would obviously be too fast. It's only with data that you can understand what's the right polling interval in order to not overload your system, but also to not be unnecessarily waiting for stuff. And by doing that, we were able to achieve a pretty significant speed up. And by running that kind of analysis, we were able to achieve a pretty significant improvement in the customer perceived performance of our system.
And as we've discussed briefly so far, Honeycomb is a platform that operates in a space that's similar to a number of other systems that fill parts of what it can provide. So I'm wondering if you can call out any specific offerings that are either available off the shelf for self-hosted capabilities or as a platform as a service or a software as a service that you consider to be the closest analogs to what Honeycomb can do, and then maybe also call out when Honeycomb is not the right tool for a specific task.
The systems we're most common compared to are, on the one hand, log analysis tools such as Splunk on the service software as a service side, or the ELK stack, Elasticsearch, Logstash, Kibana, in the category of log analysis tools. And then on the other side, people often compare us to metrics tools such as Datadog. Honeycomb is trying to help you with observability. And observability is really good for asking questions about your system. And what that means is you're really good when you don't know where the problems are yet. You've instrumented your code, you have lots of data coming in, but you don't yet know exactly what's going to go wrong. And it turns out that a lot of systems people are building these days fall into that category. People doing microservices, they're running in containers, they're running distributed systems across big fleets of stuff. They're running serverless, which, in theory makes your life easier, but actually introduces new categories of problems. So there are lots of things people are doing that are introducing complexity. And that's a world where it's really useful to be able to ask questions where you didn't know the answer up front. That said, there are plenty of worlds where you do know what's going to go wrong. If you are a media property and you've already built out your site and you've already scaled, if you launch a brand new newspaper, you probably don't have any users to start with, but by the time you've got some traffic, okay, you have 1 million readers, and you know that you're going to get this much traffic, except when there's a big news story, and then you're going to get 4 times that much traffic. And you know exactly what's going to go slow at what point. And if you're in that world, you can pretty much get away with a Mex tool. You can just instrument the things that you already know are going to go wrong, and make sure you have an alert for when that thing goes wrong. And when that goes wrong, you know what you need to do to fix it. This is also the case if you have a software system that you've pretty much stopped developing. You've finished making all the changes to it. You're not planning to add new features. You don't need to scale it up anymore. You're just ready to hand it off to an operations team to just keep it running. Again, in that case, if you're in a known scenario where the failure modes are known and understood, and the run book is easy to write, you know what you need to do in response to any given alert, then you don't really need a tool like Honeycomb in that scenario. Another example would be if your data really is unstructured, if you are emitting lots of text strings, or if you just, if your logs really need human attention, they're the kinds of things where you can't turn it into metrics, you can't turn it into structured data. You just need a human to look at every single log in order to, for example, untangle some chain of events that led to a certain thing happening. And you're at a small enough scale where you can afford enough humans to read through all of the details. That's also something where you may just want to really keep all those logs of strings and have someone go and read the things that happened at 4:30 a.m. last night.
And so it seems like Honeycomb is useful as a complement to an existing suite of metrics tracking, where you can use it for being able to prepare for the sort of fourth quadrant of the Cynefin framework, where you're trying to be able to manage the unknown unknowns and possibly some of the known unknowns, but you can then still rely on your existing metrics and logging platform for giving you the information about business as usual so that you can track that, but still be able to get alerted about anomalous information from that, but then use Honeycomb to dig into those specifics.
We love these existing tools, but the funny thing, and I guess part of our long-term philosophy, is that the knowns and the known unknowns you can usually automate. The easy problems are the ones which you shouldn't be spending human effort on anyway. The problems where you really need to know about are the unknown, the unpredictable things. So obviously we exist in a world where people have lots of tools that they're invested in, but at some point if you have humans being paged about predictable outages, then you're just waiting for things that you could have had a machine solve. If you have an outage that happens once a week or once a month, and you're waking people up for that, that's just sort of a sad use of humans. We would like people to instead make sure that they're only paging people about stuff that really wasn't expected.
And what have been some of the most challenging aspects of building and scaling and marketing the Honeycomb platform?
Definitely getting people to believe that this is a problem that they have. We come across lots of people who, as soon as they see Honeycomb, they're like, yes, okay, great, I'm finally glad I have a solution to this problem. And those people have been easy to sell to. But other people have been, we have customers who have invested large amounts of time and money into running a gigantic elk stack cluster. And they're throwing hundreds of machines at this thing, and they've thrown engineers at customizing their elk stack to work in the particular demands of their environment. And the users of the system don't really like it. The engineers who are working on it love it because it's a really interesting system to work on. It's really cool to kind of run your own log analysis system, except that that's not what these companies are. That's not the product these companies sell, right? This is entirely internal tools use case that they've decided to invest a lot of money in. And these people don't necessarily know they have this problem. They just think this is just a difficult thing to do, and the best thing they can do is throw money at it. And convincing them that no, there is a better way, that you just need to look at things in a slightly different way and invest a little bit in instrumenting your system and in changing the way that your systems talk to the world. Yeah, that's definitely been part of the challenge, is just helping people to understand where this fits in alongside the systems that they already have, especially when they've invested a lot of effort into overcoming the shortcomings of those existing systems.
So what is it about the high cardinality of the data that you're managing that makes it such a difficult problem that it hasn't been solved in a comprehensive manner by anyone else before, or at least in a satisfactory manner?
High cardinality is these terms that makes a lot of sense to certain people and makes no sense to certain others. So if you are a user of a metrics product like Datadog, you've probably come across the quote-unquote high cardinality problem. And this is the problem where, let's say you have a graph of response time, and then you have a graph of response time for each server, because sometimes you want to see if one particular server is running slow. And maybe you have a graph of response time for each piece of your web application. And then someone says, yeah, okay, but I'm only interested in this piece of the web application, but I still want to know if it's running slowly on a particular server. So now you need a graph of response time for each piece of the web application for each server. And if you have 100 servers and your web application has 10 endpoints, now you have 1,000 graphs. And then someone says, yeah, well, what about if it's running slowly when the customer is coming from a different geographic area? Okay, now you have 1,000 times 7, however many geos your company is in. And then someone says, well, which user is seeing the slowest performance? And you're like, well, I don't have the graph for that. And they're like, well, can't we just track a graph for every user? And so now you end up with 1 million users times 100 servers times 10 endpoints times, and you end up with millions of graphs. And millions of graphs has a couple of problems. And one is just no human can make sense of mixed graphs. And there's just a data management angle on the front end. Like, how do I even find the right graph to look at when I have so many graphs? And then on the back end, metrics products basically consume storage and other resources according to how many graphs you're tracking. And if you have 1 million graphs, most of them are not set up to handle 1 million graphs. Most of them are set up to, track thousands or tens of thousands. And what we're really talking about here is combinations, right? You have a combinatorial explosion of how many dimensions you need to keep track of. And that is just a problem for anything which consumes resources according to the number of graphs you're trying to plot. So that's what can be difficult about high cardinality. If the way that you consume storage is not affected by that combinatorial explosion, then you have a lot more flexibility. And this is why we store every single event. It seems like a really expensive thing to do. Can't you just roll these things up in advance into a number and then you don't need to store all the details? But actually, if you're interested in these fine-grained combinations, what if this user was having a problem every time they happen to run in this availability zone, for example? Then it's actually a lot cheaper to not have to pre-compute all of those different combinations of things if you can just ask all of that as a post hoc filter on it. So that's the high cardinality problem. Why is that interesting? Because often the high cardinality fields are, just to be clear, when we talk about cardinality, we're talking about, for some given dimension of the data, the cardinality of that dimension is how many different values can that dimension take on. So one dimension might be the HTTP status code. That's not very high cardinality, right? It can be 200, it can be 404, it can be 500. There's a few other options, but you've only probably seen maybe 20 status codes in the wild. And then a very high cardinality field is something like user ID, if you're lucky, if you have a lot of users. And it turns out the things that are most interesting to your business are usually high cardinality. The unlucky user who is hitting an edge case in your system and can never get the site to load, well, that user is permanently unhappy. And if you look at a graph of average user happiness, you don't even see that person. It looks like your site is mostly fine. But that user is going to go on Twitter and talk about how your site is always down. And if they have a lot of followers, then you have a problem there. Or if that user was going to buy something and they don't because they can't load your shopping cart, again, you have a problem. So being able to look at your most affected use is one of those cases where you can get a lot of interesting business value out of asking these questions about things that are naturally high cardinality. And that's why we think this is something that people need to understand is possible, and they need to start thinking about what questions can I ask about high cardinality fields.
And are there any other aspects of the Honeycomb platform or the underlying infrastructure that we didn't cover yet that you think we should talk about?
We try not to be too inventive with regards to our infrastructure. We've already invested some resources into building our own data store, so we try not to be too clever about the rest. We run Golang for pretty much all of our infrastructure. So our web servers run Golang, our custom data store is written in Golang. We use Terraform and AWS to manage all of our infrastructure. So we can do things like spin up new servers if we need to and spin up another copy of our environment. But we're not being very clever with auto-scaling. We pretty much know if our cluster needs to get bigger. We take a pretty pragmatic approach. We build some tools to make our lives easier, but we don't rely on them too heavily. A lot of things are just bash scripts and cron jobs, and it turns out that those things are really effective, and you don't want to mess with them.
So for anybody who wants to follow you in the work that you're doing or get in touch, I'll have you add your preferred contact information to the show notes. And as a final question, I'm wondering if you have any opinions on what the biggest gap is in the available tooling or technology for data management today.
I'd say there's a gap in the affordances of getting to grips with large amounts of data. If you have a data scientist, they can all kinds of queries with Spark or some Hadoop job, and there are lots of visualization libraries, but a lot of them are pretty much geared towards experts. And it turns out all of the questions you want to ask are not expert questions. They're more like you start with a simple question, how slow am I? And then you gradually refine that question. How slow am I on different servers? How slow am I for different users? Who are my slowest users? Let's say I found a slow user, what are the properties of that person? And whatever tool you're using, it's a difficult data presentation problem. How do I understand that? How do I see all of the different combinations? How do I get a visualization of all of the data that tells me what I want to know but is easy to manipulate? And there's been a lot of work that's gone into taking a time series and automatically smoothing it so that you can see the important details but you don't see the noise, or query languages that let you express combinations of graphs and that sort of thing. And that'll be a really interesting area to watch, to see if that can get easier to the point where people who are not expert users of data graphing libraries can use them.
All right. Well, I appreciate you taking the time out of your day to join me and talk about the work that you're doing at Honeycomb. It's definitely a very interesting product in an interesting problem space, and one that I'll have to dig a bit more into, possibly using in my own infrastructure. So thank you again for your time, and I hope you enjoy the rest of your evening.
Awesome. Thank you very much, Tobias. Cheers.